Hi, my name is Rachel Maxwell. I am a second-year graduate student working with Francis Nimmo at UCSC, and I'll be talking about localized cryovolcanism at Rhadamanthys Linea, Europa, and the role of tidal stresses. So our motivation for this is that Europa shows geological evidence for ancient cryovolcanism and potentially present-day cryovolcanism, and Enceladus has helped us understand cryovolcanic mechanisms, so we're hoping to leverage our understanding of Enceladus to better investigate Europa. So just a brief just a brief outline. I'll introduce Rhadamanthys Linea to you briefly, and then talk about the localized cryovolcanism. And then I'll discuss whether tidal stresses could be responsible for this localization, and then whether the localization could be at pull-apart basins. And then I'll sum up what we think is happening and what we plan to do in the future. So here's a figure from Fagins et al. 2000. Rhadamanthys is this one here, labeled R. It is approximately 2,000 kilometers in length, and it has a series of dark, diffuse margin patches. And we're going to use higher resolution imagery, but only for half of Rhadamanthys because that's all that's available for. So here's that higher resolution imagery. Again, Rhadamanthys continues south. You may be able to see, I'll point it out in a second, that there are these dark spots at Rhadamanthys. Here I've highlighted them in red. And as per Fagins et al. 2000, low albedo margins at triple bands may be indicative of intrusive or explosive volcanism. So if these spots are cryovolcanic, we're wondering why they're localized. So today I'll discuss two possible mechanisms for the albedo localization. The first is using tidal stresses, and the next is using strike-slip motion. I'm not going to discuss other potential mechanisms today, such as like the feedback between local vent and cooling rate, or local vent width and cooling rate. So let's start with tidal stresses. Where there's a localized maximum normal stress, the vent widens, allowing for potentially more cryovolcanism to occur. This is similar to the mechanism seen on Enceladus, as discussed by a number of authors. So when I say tidal stresses, I mean the stresses that are occurring throughout the orbit. So here are some slides that I've borrowed from Francis, where we're at pericenter, and we see that the faults are almost entirely in compression. And as we move about in the orbit, the faults change between compression and tension. So now that we're in the apocenter, it's primarily in tension, so the faults are pulled apart. So as I said, when the fault widens, that could potentially allow for more active cryovolcanism. And I've borrowed some figures from Porco et al. 2014. On the left here, we see observed jet activity, where yellow is higher rates of jet activity. And on the right is maximum normal stress, where yellow is higher normal stress. And we see that the areas with higher normal stress correlate pretty well with higher rates of observed jet activity, suggesting that this is a cause of the jet activity. So at Rhadamanthys Linea here, I digitized locations on the fault, and using a method from Hereford 2009, found the maximum normal stress. And here are all of the points that I used, and here are just the points where the maximum normal stress is greater than 80 kilopascals. And here the red dots are the dark spots. So we see that the maximum normal stress tends to correlate pretty well with the areas of the dark spots. So this suggests that there's a mechanism happening here that's similar to what we see at Enceladus. So that's great. Now let's take a look at the strike-slip motion as a potential mechanism for the localized cryovolcanism. So when I say strike-slip motion, I mean specifically tidal walking, which produces pull-apart regions. And this is expected to drive left lateral motion at Rhadamanthys. So just to go over tidal walking real quick, tidal stresses can produce strike-slip motion known as tidal walking. And this can be either right or left lateral depending on the fault orientation and the location of the fault on the surface. And since Rhadamanthys is predicted to have a left lateral motion, that's what I'll show here. So here we have a fault. The fault opens. There's a left lateral motion as you continue around in your orbit, the fault closes, and then when right lateral motion should occur, it's instead impeded by friction. So there's an overall net left lateral slip, leaving a pull-apart basin here. And so these open faults could allow for localized cryovolcanism. So in looking at this image, I found four pretty good examples of left lateral strike slip motion. I'm going to focus on just this one here. So here we see this band that has a left strike slip motion at the location of Rhadamanthys. So what I've done is separate the image into two different plates, more or less. And then I colored them in different colors so that it'd be easier to see where they pull apart or push together. And I've highlighted where some of the dark spots are located. So now when I reconstruct the plates, we see that there's a white area here. But since this is going back in time, what that really is compression rather than tension. So that's sort of a strike against the tidal walking mechanism as being a cause of these dark spots. But if we want to look at all of the dark spots that we've seen, we can figure out where the pull-apart basins should occur, and the pull-apart basins would provide preferential pathways for the ascent of cryovolcanic material. And so since pull-apart basins occur when the local fault orientation is different from the main orientation, we can predict where these pull-apart basins should occur. So here I've plotted the angular deviation from the local fault orientation to the background fault orientation, and I've used two different background fault orientations labeled here in white since the fault changes orientation. And then here I've plotted those angles that are greater than 45 degrees, which represent tension, or less than negative 45 degrees, which would represent compression. And we can see that while some align okay with where the dark spots are, they really don't correlate as well as the normal stresses did. So if we compare the maximum normal stresses with the angular change in direction, these correlate much better with the dark spots than angular change. So this suggests that the localization of cryovolcanic activity is likely due to high maximum normal stresses, which is seen on Enceladus, so that's promising. And in the future, we'd like to consider other feedback mechanisms, such as local vent width and cooling, and the cooling rate as exacerbating or inhibiting cryovolcanism. And then we'd also like to incorporate other stresses, because here we just use the tidal stresses and non-synchronous rotation. And that's it. So I'll take questions.
This is a very intriguing presentation. What I've always wanted to know, though, is how come we really only see these spots at Rhadamanthys? And what are your thoughts on how to explain the dark margins of, the continuous dark margins of other so-called triple bands?
So I have no idea. When Francis, I've been working on this project for maybe 3 months. So when Francis introduced this project to me, he was like, look, this is weird. They're in different spots instead of like all over the place. So I don't know. That's something that I'd like to learn more about. So.
All of the work that I've seen so far, everybody keeps analyzing the stress conditions on two-dimensional lines, except these faults are three-dimensional planes. Did I lose my microphone? And none of these faults are vertical, and they're intersecting in three-dimensional space. And so I'm not at all convinced that we can take the surface trace of any fault and run it through stress orientations and predict where it would erupt, because you're only looking at a single slice of a three-dimensional fault network connected in the subsurface. And so I question in general, it's not just your work, because this is how we've all been doing it, but it's not how we find oil and gas on Earth. It's not how we drill for water. We don't just look at traces on the surface and then guess. So I'm just want to throw that back generally to the audience. It's not to you. As you say, you've only been working on it 3 months, but right. I think that's part of the reason why you're not getting a great correlation. is because you're looking at it two-dimensionally rather than three.
Right, that would make sense.
Danielle, I think that the presumption for these thin ice shells is that the faults are in fact vertical. They're like mode 1. Anyway, so I was actually going to go back to your future work. I mean, you know, on the Earth, you know, if you have a fissure, they often evolve to a single vent or back. I mean, you know, I know, I'm sure you know this already. So it's like, it's not all controlled by external tectonic forces.
Right, yeah.
There's a lot of that's going on at the vent itself.
Right, yeah. So that'll be the next step that we're doing, is looking at how like the cooling and stuff could potentially single it off into one
Yeah, that's
area.
why we have volcanic throats and all the rest of that good stuff.